Hey, AP Chemsters, this is Mrs. Vanderwille, and should be the third and the last installment of Section 17.2. Then we'll go on to Section 17.3. So this is a summary of everything we have done so far in Section 17.2. So this summarizes the complete description of a galvanic cell. The first part, we should already notice that the cell potential is always positive for a galvanic cell. Therefore it's spontaneous. It will do it on its own. Part B says the direction of the electron flow. You should tell us how it goes. It always goes from anode to cathode. Letter C, show me what the anode and cathode is. And letter D, the nature of each electrode, the ions present in each compartment. Now what happens is, we're going to see in a little bit, what happens if one of your oxidation occurs. If you don't actually are using the metal itself to be oxidized. What happens if you have an ion being oxidized into another ion? There you would need to use something like platinum, because it's inert. It will not take place in the redox reaction if none of the other ones are going to react as they're solid. Excuse me. So anyway, in problem number 7, it says calculate the cell potential for the following reaction. And here is our line diagram. And what we need to include is to draw the diagram of the galvanic cell for the reaction and label it completely. Well, hopefully you have a little better time of that than I will, because you know me and my smartboard is not probably going to work out too well. So how are we going to attack this problem? They gave us the line diagram. And what do you remember is true in a line diagram? So in the line diagram, hopefully remember this, that the anode is always written first and then the cathode. So if I know what the anode is, then I know what is being oxidized, and I'll know what's being reduced. So the next thing I need to do is now label my beakers. All right, so here is my pour attempts at beakers, okay? And let me put in my 2 electrodes, and let's hook them up. And here's my voltmeter. And don't forget your salt bridge, because that's how your negative ions are transferred from one beaker to another. And here are my beaker solutions. I love my smartboard. And now actually let's label this my anode and this my cathode. So what's happening at my anode? I have this metal bar. Right here is my calcium apparently, and it is being oxidized into calcium ions. So what's happening at my cathode? Let me use red, because after all it's red cat, isn't it? And so this bar is my silver bar, and I have silver ions in solution. So now what do I need to do? I need to label the flow of electrons. Well, over here is my anode, and as we know, my calcium is going to lose its electrons, and so the flow is going to go this direction, and where the electrons will be actually deposited on the cathode. And don't forget, you're going to have more electrons going through the salt bridge. It's probably your nitrate ions or whatever you made your silver solution out of. I believe I am done with my diagram. Now I actually have to calculate the cell voltage. All right, so let's do my silver first. So silver ion is being reduced to make silver metal. So I'm going to be plating out more silver metal on my cathode. And when I look up silver, it is going to be the E naught of the cathode is 0. It's an 80 volts. That's a point in there. There it is. And let's do my oxidation. That's my reduction. Let's do my oxidation. And what will that be? That will be your calcium losing 2 electrons to make the calcium ion. And the E for the anode here is equal to negative 2.76. It's a negative 2.76. There's a negative right here if you can't see it. And so let's go ahead and, oh, wait a minute, I got to balance my top reaction here, because my electrons, I have 2 electrons here and 1 here, so I need to multiply that by 2. So I have 2 silver ions plus calcium yields, 2 silvers plus 1 calcium, 2 plus. My E naught for my cell ends up being looks like 3.56 volts, if I did that right. I think that's everything they asked for. Now the next one is what I was referring to earlier, where you do not have a solid at one of the electrodes. So we need to do the same thing here, describe completely the galvanic cell based on the following half reactions. So obviously the first thing I need to do is decide which one is being oxidized and which one is being reduced. So if you look up these numbers on the chart, why don't you do that right now? All right, hopefully you found where the silver ion is 0.80 and the iron 3 plus is 0.77. So they're both positive numbers. What do we need to do? Do you remember what we said? The one that is least positive will be oxidized. So the iron is your anode because that's where oxidation occurs. So your silver is at your cathode, red cap. So let's draw these beakers now. Ready? Let me make some colors here. And so my anode, now wait a minute. My anode doesn't have a solid. There is no solid with the iron. It's an iron 3 plus ion and the iron 2 plus ion. What do you do? Well, you have to use, let's say, platinum. So here's my platinum cathode, or excuse me, my platinum anode, my mistake. And let's see here, I'm going to have my silver cathode, and I'm going to connect the two, and here's my voltmeter, is going to be right there. And I still need a salt bridge, so let me make my salt bridge. Oh, and don't forget, we need to have my solutions in here. So what's going on here? What's in my anode beaker? Well, I have some Fe3 plus ions and some Fe2 plus ions, probably 1 molar at this place because we don't know anything besides 1 molar. And I still have a 1 molar silver plus ions. Okay, so my direction of my electrons are going here, and the electrons are going to be deposited on the silver metal, and then your nitrate or whatever ions you're working with will go through the salt bridge to complete the circuit. Okay, so now what do we need to do? We need to balance this out. So my reduction is where you have the Ag plus E negative makes silver, and that's equal to 0.80 volts. And my oxidation is going to occur with the Fe2 plus losing an electron to make Fe3 plus. And that is equal to, make sure you put your negative in there, 0.77 volts. And so your E for the cell is end up being a measly 0.03 volts. That's not very positive, is it? What about my balance equation? Do I have to do anything funky with that? No, because I still have 1 electron and 1 electron. I don't need to do anything funky. Oh, I didn't need to do that. I meant to do Fe, not there. Okay, so Fe2 plus makes Ag plus Fe3 plus. So how do I do my line notation? Well, you have to put your electrode in for your anode, and that electrode happens to be the platinum. Now, what's platinum in solution with? It's in solution with iron 2 plus aqueous, and that's at 1 molar, and iron 3 plus aqueous, and that's at 1 molar. There's my cell bridge. Holy cow, I'm going to run out of room. And now you write the silver ion solution, and that's at 1 molar. And then here's your silver. That's an Ag, by the way. I love my smartboard. Solid. So that's how you do the line notation. Sorry, it's a little bit messy, but you know how much I love my smartboard. All right, let's go on to the next problem. Wow, I got so excited. I thought there was more. This is actually the conclusion of section 17.2. So why don't we go ahead and stop this, and I will make up the next one. We'll see you later.